Let's have a look at parametric equations. So one of the first things you might want to ask about parametric equation is what's its domain and range. So remembering that domain is just a set of x values we can put into a function. Let's consider that. So when we're looking at what can we get out of a function, the first thing we need to consider is what kind of function do we have. Here we have a cos function, which we know is usually limited between 1 and minus 1. However, we're only allowed to plug in values of t between 0 and pi over 2, which in this case, because we're doubling t, will take us up to pi in the regular graph. Okay, so it looks at first like we can still get all of the values between 1 and minus 1 out of this. However, we're not actually allowed to plug in pi over 2, so we'll finish just shy of there. That can take values from 1 inclusive down to minus 1, not quite including it. So we can see that x, 1 take away 1 is 1, will be its lowest value, and we are allowed to plug in 1. The highest value it can take is 1 minus minus 1, 2, but we're not quite allowed that, so it can't actually equal 2. Now let's consider tan to get the range. Well, if we look at the tan function, we know it looks something like that, with an asymptote at pi over 2. So we know that we can get 0, but there is no upper limit. So there you go, just by considering the type of function we have and what values of t we're allowed, we've got the domain and range of this function. Okay, now let's consider the actual Cartesian equation of this. So another thing they might ask you for, they might ask you to find the Cartesian equation of a parametric. What that means is find y in terms of x, or vice versa. They'll usually tell you what form they want it in. They might, for instance, want y squared equals some function of x. So let's go looking for y squared as a function of x. Well, first of all, we'll need to figure out what y squared is. Y squared is equal to tan squared x. But now let's just have a think. X is defined in terms of cos 2t, so it's not easy to get tan from that. However, it is easier to get sines and coses. So maybe if we write y squared equals sine squared t over cos squared t, maybe this is a better way to look at that function. Okay, so we've got that. We want to find out what is sine squared and cos squared in terms of x. We need to change cos 2t into just sine or cos t. That's convenient because this has 3 different forms. Choosing the form with just coses in it, we can simplify this and see that x is equal to 2 minus 2 cos squared t. Therefore, cos squared t is equal to 2 minus x over 2. Perfect. And what about sine? Well, we can choose the other form of cos 2t, 1 minus 2 sine squared t, which gives us 2 sine squared t is equal to x, dividing by 2, sine squared is equal to x over 2. Excellent. So now we can rewrite this as x over 2 divided by 2 minus x over 2. The halves cancel on top and bottom, leaving us with x over 2 minus x. Cool. So you've seen how to get the Cartesian equation. Try and write y in terms of x, probably using some trig identities along the way. Domain, we just need to find the domain, the set of values x can take, given the set of values that you're allowed to put in for t, and similar for y. Consider them both separately. Okay, final thing that we'll do is we'll differentiate. We'll find dy dx for this function. Okay, doesn't actually require anything we've done before. You could do this completely independently. So if we want to find dy dx, we're going to start off by just finding dx dt and dy dt. Because it's easy to differentiate x with respect to t, because we know how to write x in terms of t. So let's do that. That's going to give us 2 sine 2t, and tan becomes sec squared t. So how do we find dy dx? We're probably spotting by now that once we've got two different types of derivatives, we can use the chain rule to manipulate them into what we want. Dy dt divided by dx dt, or to see it a nicer way, multiplied by dt dx. Again, imagine those dt's cancel out, will leave us with sec squared t over 2 sine 2t. We've got our derivative. Maybe we want to tidy that up. That doesn't look very nice at the moment. So we could write this if we wanted as sec squared t half cosec 2t. Again, we don't need trigonometry written as denominator anymore. We have a function that can write that. And it was over 2, so we still keep that factor of a half in there. That's pretty much all you need to know for parametrics.